Good afternoon, good evening, everybody, and welcome to a special edition of SETI Live. My name's Simon Steele. I'm the Deputy Director of the Carl Sagan Center here at the SETI Institute in Mountain View, California. And I'm joined today by my colleague from across the building, Dr. Becca Robinson, who is a heliophysicist and outreach lead for the MUSE mission. Maybe we'll say a little bit more about MUSE later on. But we're going to start, Becca, talking today about weather. Now, it's a beautiful weather here in Northern California. We'd be very interested to hear what the weather is like where you're tuning in from. But we're talking about space weather. That's weather up there in space. What is space weather, Becca?
Good question. So space weather is generally defined as anything that impacts our atmosphere, but above our normal weather level. We are not the only planet that experiences space weather because it comes from the sun. So we're, of course, not the only planet that experiences the effects of the sun. We are just one of many planets that experience space weather effects. The sun is constantly giving off a steady stream of plasma and radiation, and we are affected by that. Fortunately for us here on Earth, we're also protected by that, by primarily our magnetic field. So we've had some interesting space weather over the past few weeks, and we are excited to talk about it.
Yeah, so there's something dramatic happening up there. It's a little bit of a storm season, isn't it?
Yeah.
And we talk about seasons for weather down on here on Earth. Are there seasons for space weather?
Yes, there are. So there are a couple of them, actually. One way to think about this is actually something that aligns with our Earth seasons. Our Earth seasons are a result of the Earth's tilt, right? It's not necessarily how close or far away we are from the sun that makes summer and winter. It's not that. It's whether we're tilted towards or away from the sun. And during the spring and the autumn, we are neither tilted towards nor away from the sun. And that means that our magnetic field tends to be parallel to the sun's magnetic field. Space weather is a magnetically driven thing. It is driven by the sun's magnetic cycle. So another seasonal effect of this comes from the sun's magnetic cycle. That's about an 11-year cycle where we experience a maximum of solar magnetic activity, which is right about now, and a minimum of solar magnetic activity, which we'll slide into over the next couple of years as things evolve on the sun. So there is some seasonality there, and we happen to be in the crux of both of those ideal, I suppose, if you're a space weather enthusiast, those ideal seasons. We are both near the autumnal equinox and in the solar maximum of its magnetic activity.
So this is a perfect storm, you could say.
I think so.
Yes. So what's happening here? You know, a lot of viewers will be familiar a little bit with the sun and the activities in CME's coronal mass ejections. And of course, let us know where you're tuning in from. Let us know what the weather's like when you're tuning in from. And of course, pop comments and questions into the chat, and we will get around to answering those. So I've forgotten what I was asking now. Yes, this perfect storm we're having. Should we start at the sun where it all begins?
Yeah.
Okay.
Let's start at the sun. I think that this is worth talking about, and the reason that we're having sort of a special edition of SETI Live. I mean, space weather events are not all that special during solar maximum. We sort of expect them, and it's weird if we don't get them. And so you may have noticed an uptick in good auroral geomagnetic storms, auroral substorms, and impacts that we've had on our magnetic field and our atmosphere due to the sun's magnetic activity over the past several years. This one was weird, though. Beth, could you pull up a picture of the sun's coronal hole with no magnetic field lines? Thank you. So this is the sun on, I believe this was September 13th or thereabout. So about 3 weeks ago. This is a picture taken by the Solar Dynamics Observatory's Atmospheric Imaging Assembly, which measures light in extreme ultraviolet. Now, the sun's atmosphere glows really brightly in extreme ultraviolet light. So that's what you're seeing here. All of those bright spots are places where the magnetic field is connected back to the surface in a loop. And so we're seeing sort of some of the magnetic loop activities and some of the hot plasma associated with moving magnetic fields in the sun's atmosphere. But what you're also seeing is that gaping black hole. Interesting. Typically, when we're looking at space weather events, they come because of large ejections and explosions driven by magnetic reconnection on the sun's atmosphere. So typically in those bright spots. But this particular storm and these subsequent substorms that we want to talk about came from that dark spot, not an explosion, not what's called a coronal mass ejection. This is called a coronal hole.
So just hang on a second. So this is the sun. The sun is very bright and it's
Very
yellow. And now
much
this is an ultraviolet image. This is very high energy. And the surface of the sun here is, we've heard about black holes. This is a just this dark splodge on the sun, which is bizarre in itself. So why does it look black?
It looks black because it's a little bit cooler than the surrounding plasma. That doesn't mean that it's cold by any stretch of the imagination. It's just that in this particular wavelength, the brighter spots, it's tracing about 800 to a million degree plasma. And the plasma inside of that coronal hole is not quite 800,000 to a million, 800,000 rather, to a million degrees. It's going to be a little bit cooler there, except for a couple of bright speckles in the middle where maybe some exciting things are happening. But what's interesting about the coloration of this wavelength as well, I mentioned that the bright spots tell us where the magnetic field is connected back to the surface. And generally that's associated with magnetic explosions. In coronal holes, the magnetic field is not immediately in our local space connected back to the surface. Beth, could you pull up the magnetic field image I have with the coronal hole? Yes, this is that same coronal hole a couple of days before the last image that we saw. I believe this was September 11th. And this is what's called a potential field extrapolation of what the magnetic field might look like. Now, it's not a very... It is sophisticated code that goes into calculating this magnetic field, but it's not really, it's in a way one of the most simplistic extrapolations of a magnetic field, one of the most simple solutions to the magnetic field here. And if you look in that coronal hole, you might see lines that are coming out of it, but then just kind of end somewhere, right?
Yeah, which is not good because we don't want to know.
Why doesn't that make sense to you, Simon? Why is that making you feel uncomfortable?
Well, we like magnetic fields. We like to see them come out and then go back in again. Magnetic fields should have a north and south pole, and you see these big loops coming around, and when things just go straight out in one direction, that's worrying to me.
Right. This extrapolation doesn't really capture fully what the sun's magnetic field is doing in that coronal hole. Coronal holes are not regions where the sun's magnetic field is zero or necessarily super weak. It has magnetic field there, but it's just that the magnetic field there is open to interplanetary space. And so it acts sort of as a magnetic superhighway for plasma. And that's why in this particular extrapolation, the lines just kind of seem to end in space. That's not physically true. What is physically true is that we're close enough to the sun such that those magnetic field lines are open with respect to us. Those field lines are pointed out into interplanetary space. Now, because we require and because we observe magnetic fields to have both a north and a south magnetic pole, it must connect sometime and someplace back to the sun, right? We know this. And what's happening here is that open magnetic field lines that are that long, they will come back around eventually. It's just that we're too close to the sun to be able to see that.
So how far are they going? We're sort of 150 million kilometers, one astronomical unit away from this star. How far could these lines be whipping out before they loop around and come back again?
They could be looping around super, super far from us. The sun's magnetic field fills and expands beyond the entire solar system. It's what we call the heliosphere. And so those magnetic field lines have the potential to go as far as the outer planetary orbits or the things that are past the orbits of Neptune and Pluto. So it's altogether possible that those field lines are much, much longer than the solar system is. So that's why we're sort of seeing a weird extrapolation here. It doesn't quite fit in with what this extrapolation is trying to tell us. It tells us better things about those closer, lower lying magnetic loops in the near corona, but not what's happening in the heliosphere, not where that coronal hole is stretching out to.
Right. So we're going to get back to saying what's happening. What is this thing doing to us? In a second, I'm going to welcome some people tuning in from Sweden. We've got Eduardo from Buenos Aires. We have Toronto, Paul. Hi, Tommy from Norway. From the Netherlands, Peter, Halifax, Nova Scotia. It's raining, according to Peter. Oh, that's Peter, probably from the Netherlands. It's raining in Holland. We've got Northern Virginia. We have Oldham in the UK. It may well be raining in Oldham too. So thank you, everyone. We'll read out some more in a moment. But so we've got this cool region of the sun. Looks like a mega sunspot. We've got magnetic field lines basically aiming straight out at us, and that, you say, is this sort of particle superhighway.
Yes. This is something that is really exciting to space weather enthusiasts, particularly aurora chasers, because while we typically are looking for those magnetic explosions that send plasma to us, coronal holes also allow high-speed solar wind to just hitch a ride on that magnetic superhighway straight to the Earth. And that's exactly what happened with this coronal hole. It sent high-speed solar wind directly to the Earth, which is super exciting if you're looking for space weather. Now, there is one caveat and one thing that made this space weather that resulted from this coronal hole particularly strong. And that is the direction of the magnetic field of that plasma mass coming in from that magnetic superhighway. Now, this is true for coronal mass ejections as well. We need the magnetic plasma coming in from the sun to be pointed in a certain direction as it approaches the Earth's magnetic field to get intense space weather and to get the potential for intense auroral substorms, right? Have you ever tried to stick two north poles of a magnet together, Simon?
I have.
Was it frustrating?
It's very frustrating. Yeah.
Why is that?
It's always bothered me. It's weird, the magnetic fields. Fields are weird anyway. Magnetic fields. So, this idea of having this sort of invisible repulsive force is extraordinary. But
exactly.
Yeah.
Well, we have sort of a northward facing magnetic field on Earth today. And so if we have plasma coming in from the sun that also has a northward facing polarity, do you think it's going to connect to our magnetic field very efficiently? No, it's not. And so typically what aurora chasers look for is a southward facing magnetic component to that plasma coming in so that it reconnects efficiently with our northward facing magnetic field. The frustrating part is that the direction of the magnetic field can change a bunch of times on the way from the sun to the Earth. So it's hard to predict. But in this case, what came in from this coronal hole was a southward facing magnetic polarity from this high speed solar wind. So you've got the kinetics and you've got the magnetics to ensure really efficient magnetic reconnection with our own Earth's magnetic field. Now, the other thing is that this happened about a week out from equinox, right? What we're looking for, when I say efficient magnetic reconnection, what I mean is I want one magnetic field to be pointing pretty much exactly up and one magnetic field to be pointing pretty much exactly down. If we have a planet that's tilted toward or away from the sun, that's not really what we're going to get, right? Because we're not parallel to the sun's magnetic field. But during the equinoxes, we are parallel. And so that ensures a much higher efficiency of reconnection, and it can lead to much stronger geomagnetic storms, which is exactly what we saw coming from that coronal hole. Does that make sense?
It does. And I have a question though. We heard a lot about coronal mass ejections, which are magnetic recombinations that send out this sort of plasma, bolt of material flying out, which is reasonably short-lived. The structure here is this is a longer lived event, isn't it?
Yeah. So coronal holes tend to evolve and sometimes last longer than a solar rotation. It's, of course, difficult to observe them on the far side of the sun unless we have a spacecraft on the far side of the sun, which sometimes we do. We have Parker Solar Probe and we have the European Solar Orbiter that are sometimes on the far side of the sun with respect to us, but we don't always have the luxury of those observations. So tracking the evolution of these coronal holes, I think, is a science endeavor that is only getting better with the amount of instruments we have in space, and with our ability to use big data sets to train machine learning algorithms to sort of predict what the most likely evolution of those coronal holes will be when we can't see them. But that being said, they very often last more than one solar rotation. And this one, being so large, lasted quite a long time. And the longer it stays sort of relatively in front of us and facing us, the higher likelihood we have of big effective space weather events, because it's constantly sending that solar wind out to us. So you're right, it's not just the short-lived magnetic reconnection of a CME. This is, weeks of constantly facing coronal holes.
Nice. So let's take this journey from the sun. This stuff is coming out, and it runs into us, and of course, what it does, it provides this incredible auroral show, the northern lights, or the southern lights if you're down in the southern hemisphere, and that's beautiful. But there's also a lot of science in that, isn't there? So as a heliophysicist, this is your realm. Tell us, when you see an aurora, apart from sort of gasping and over the amazement of how beautiful it is, what do you do then? What do you unpack in your tool set to examine an aurora?
So my experience with aurora chasing is primarily done in the Norwegian Arctic. And I know we've got some Norwegians here, so hi. How are we doing? So I have spent a lot of time in the Norwegian Arctic looking for auroras and piecing back the puzzle piece of what happened to generate those auroras. Norway is situated in a latitude band where they're very, very likely to see auroras, because when that magnetic plasma comes from the sun and reconnects effectively with our magnetic field, those particles can then spin down our magnetic field lines and end up in our atmosphere, a layer of the atmosphere called the ionosphere. And it creates disturbances on the ground based on disturbances, A, to our magnetic field, and B, to the ionosphere. Norway is full of stations that recognize and measure those signatures in real time. So the first thing that I always look for if I'm determining whether or not to get out of bed and go outside to look at the auroras are magnetometers. Now, these are instruments that measure blips and disturbances in our local geomagnetic field. So Beth, I think I have a stat plot of magnetometer readouts, the one that said it's a GIF and that it's not. Yes, this one. Okay. So this is called a magnetometer stack plot. This is taken from, I pull it from the University of Tromsø Geophysical Observatory website. And each colored line that you're seeing is a different station all the way down the Norwegian line. Now, what's happening in Norway isn't necessarily always what's happening or will happen over North America, but sometimes it is. And in this case, the ensuing geomagnetic storm was long that everybody got aurora all over. I'm just going to take this top line because this is in Neolus and this is up in Svalbard, an island very close to the North Pole. And do you see this? Actually, I don't know if they probably can't see my cursor, can they? But there is a dip right in the beginning of that line. If you read it from left to right, there's a dip down. And if we go towards the center of this plot, there are a lot of dips and a lot of disturbances. Those disturbances are smoking gun signatures of the onset of auroral substorms. Whenever you see a magnetometer plunge like that and then eventually recover, what you're seeing is essentially evidence of, if you were to look outside, you'd probably see auroras fluttering over your head. And so I'm always looking for this sort of downward disturbance in the local magnetic field. Now, over in the top right-hand corner, you'll see a scale. That's a length scale that you can sort of map onto each of the disturbances. That's a 200 nanotesla scale. And during a storm that's as big as this one, the disturbances are too large for the normal scale. The normal scale is usually on the order of tens of nanotesla. This storm was so big that 200 nanoteslas is that tiny little scale up there in the corner. So if you were to map that onto these disturbances, some of them are well over 200 nanotesla disturbances in the local magnetic field at that station. And that's a big deal. That is when we're getting hit by tremendously powerful magnetic plasmas, and that is sending a ringing through our local magnetic field. So when I am looking to see whether or not there are probably auroras, this is the type of stuff that I want to see, essentially.
Okay. So can you just the Earth has a magnetic field, and you're talking about nanoteslas. What is there some way we can think about how strong that is?
It's relatively weak, actually.
Yeah. Okay.
I suppose if you were to think about like a magnet to the refrigerator, these are relatively weak fields. However, the scale on which they dictate everything around us, and the scale that they have, or rather the dictation power that they have over a tiny particle is quite significant.
Okay.
And so for space weather language, 200 nanotesla is just insane, but we're not going to be, harmed by something like that necessarily, by those magnetic field strengths.
Okay. But we are going to be wowed by them.
We're going to be wowed by them. Yeah. And the second ingredient in this auroral substorm recipe is having a bunch of electrons dumping into our atmosphere. Those electrons are what are actually reacting with the particles in our atmosphere to give off that light. So Beth, I also have the plot of Scandinavia with the mean Rhody and the total electron. Yes, thank you. So this is by the Norwegian Mapping Authority, or Kartverket, if you're in Norway. Rhody stands for rate of total electron content something. Basically, the total electron content in the ionosphere is usually pretty constant until we get this extra dump from the sun, in this case. And the redder this map, the more change there has been in the amount of electrons that we're seeing in the atmosphere. Now, you may see behind those colorful splotches, there's a map of Scandinavia. That's because all of the base stations for this map are located in the Nordic countries, basically. And so what you can see is in northern Norway and Sweden and in much of Finland, there has been a huge dump of extra electrons, that's by those dark red splotches there, into the atmosphere above those regions. And what that tells me is that a huge amount of solar plasma has made it down the magnetic field lines as it's disturbing those magnetic fields, adding electrons into the ionosphere and interacting with the particles that live there, which eventually gives us the northern lights. Does that make sense?
It does. No, the reason those regions are red is because you have detectors there. Of course, that red line, I presume, would follow out east and west from there, because this is going to be a circumpolar ring.
Yes.
At that altitude. So if you head out over, just above the Shetlands in the UK, you'd still get the red going out that far, and then it would progressively go down to the green and the blue.
Yeah, and the more intense this dump of electrons, the stronger the auroral oval pulls south. There's a lot of atmospheric drag that comes with geomagnetic storms like this. And so the more powerful that electron punch, the more southern latitudes are able to see the auroras that do there.
Great. Amazing. So before we start taking questions, and got a few more people tuning in, welcome from Massachusetts and Dallas and Germany, Austin, Texas, greetings, and France as well. Let's have a look at the end product of this coronal hole, sending this stuff out. Let's see what it looks like.
Yeah, we've seen the data from this storm. Let's see the results of this storm. So the results that I actually have are images from my friend Vincent Ledvina up in Fairbanks, Alaska. He is also known as the Aurora guy. So if you search up the Aurora guy, that is him. And he's graciously sent some videos from Fairbanks, Alaska. So again, Norway, Scandinavia, the Nordics, they all got this storm, and so did Northern North America in this case, because it was so intense and so long that several substorms of aurora happened. So Beth, feel free to pull up any one of Vincent's videos.
Hey, look behind you too.
Oh, wow.
These were so great.
Yeah.
We saw a couple things here.
Here it comes.
I won't talk over Vincent.
Oh yeah, look at that. Good substorm action. Big westward traveling surge there.
Do you want to pause that for a second, and then we can, Becca? What are we seeing here? These sweeping arcs of green.
Right. So Vincent did mention there is a westward traveling surge there. That's sort of what you're seeing. Auroras, they come in many different forms. And what you're seeing a lot, or what folks saw a lot in this storm, were a lot of those discrete arcs and surges as they sort of move along the sky. You can also see how sort of hazy it was in Alaska that night. So I don't know if that's haze because the sky was all glowing, or haze because it was actually hazy, but that's just a testament to how strong this storm was. Now, the typical green that you expect and that we see a lot of here, that is from electrons hitting that middle layer of the ionosphere where oxygen and nitrogen live. So you've got electrons coming in and hitting one particle and then bouncing off to another particle and giving off this green emission. And that's sort of an easy wavelength of light for our eyes to perceive. And so in the darkness, where there's not a ton of light and where the only light source perhaps is the northern lights, green is going to be really easy for us to see. And so typically folks think of the northern and southern lights as green. However, there are a couple little flutters of purple in there. There's some, I guess, kind of in the middle of this screen. And you tend to see purple when the electrons are able to punch deep into the lower altitude of the ionosphere where molecular nitrogen lives. And so the interaction between an electron that makes it that far into the atmosphere and hits a molecular nitrogen, that's two little nitrogen particles stuck together, that emits that purplish pinkish light. And typically, if you've seen a lot of auroras, that tends to happen when you get a powerful dump of electrons that creates a lot of movement in the auroras as well. You get some fluttering and undulation there, which is definitely what they were seeing up in Fairbanks for this storm too.
Yeah, that's beautiful. Let's take a couple of questions here from the chat. One from Terrence. The difference between a solar flare and a coronal mass ejection.
Excellent question. This is so this goes back to how we define what we're seeing. A solar flare is the brightening that comes from a magnetic reconnection event that would or would not have launched a coronal mass ejection. So the flare is the radiation, the brightness, the light. Typically in visible light, sure, but mostly in X-ray and EUV light. Very high wavelengths of light. The coronal mass ejection are the particles that are ejected. So that's the plasma that's ejected from this magnetic reconnection event. Magnetic reconnection, being one of the driving forces behind these things, is very powerful if you have efficient high angle reconnection. And that essentially translates that magnetic energy into light that we can see, heat that we can detect, and particle acceleration. So the flare is the electromagnetic signature of what's happened. And the coronal mass ejection are the particles that are ejected from it.
Nice. A couple of people have mentioned the Carrington event. Tommy has, and Terence did as well. Can you say a little bit about what that is, and what would happen if we had another Carrington event?
Yeah, so the Carrington event, for those of you who don't know, was back in 1859. The sun released an enormous coronal mass ejection, which had, much like this coronal hole storm, very favorable reconnection with the Earth. And it was such a strong geomagnetic storm that there were auroral substorms visible as far south as Colombia and South America, and as far north for southern lights as Cairns, Australia. And so truly it was only the equator that didn't necessarily report northern or southern lights, right? So that is intense. And the prevailing technology at the time were telegraphs. Okay. Why is this important? Because not only do currents coming into our atmosphere create things happening in our atmosphere, right? Electrical currents and northern lights and aurora and stuff like this, but these currents can also induce ground currents in the Earth's crust. The lithosphere is highly conductive. And during strong storms like this, induced currents can actually come up from the ground. That's not what you want if you have an electric thing grounded to what is normally the ground voltage, right? And so if you've got an extra induced current, you're going to get zapped, essentially. And that's exactly what happened. The telegraph operators were ending up in the hospitals reporting burns and zaps and reporting telegraphs sending left, right, and center without actually being connected to an external power source. That's how strong this was. Now, the equivalent to that today would probably obliterate our electrical grids because we don't have infrastructure that is robust to that amount of current coming into our ground or being induced in our ground system. So the estimates currently go into the billions, if not trillions of dollars to fix. And one estimate that I heard in terms of time to fix our electrical infrastructure was 4 years minimum. Now, we did a pandemic that is still affecting us, of course, but we went into lockdown for a couple of years. Can you imagine total darkness for 4 years? I can't.
Yeah.
So this is something that is essentially always a threat. Now, the dirty secret, I suppose, in heliophysics is that we're not super good at predicting when and how powerful flares and coronal mass ejections are going to be. So to address that problem, we have computer simulations, sure, because we can get high resolution sort of boxes of plasma that sort of acts like the sun, and that's great, and we can do things on those time and spatial scales. But we need better instruments to actually observe the actual sun. And so to that end, the team that I work for is building an instrument called the Multi-Slit Solar Explorer. And it is being built to do exactly that. It is being built to get better at understanding the solar corona. And so what it is it's a way of looking at the sun's atmosphere in details that we have, at least spectroscopically, that we haven't really been able to do until now. And what we're going to do is get a much better time series of spectral information as these things erupt. Now, we have spectral information of eruptions in the chromosphere from MUSE's big sister IRIS, which is in space now. But IRIS is an instrument that's called a single slit imaging spectrograph. So what IRIS does is it takes a single slit mask and it scans the sun like this for interesting exploding events, right? But the problem is that with only one slit mask to collect the spectrum from the light, if you're scanning over here, inevitably something exciting is going to happen over here. By the time you get back here, something exciting has gone off over there. So it's difficult to get a good space-time understanding of what's happened. And the reason we need spectra is because spectra provide the physics behind the light that's being emitted by the sun, right? It can provide the temperature of the plasma, it can provide the relative speed of the plasma, and it can provide information about the turbulence of the plasma. So we need spectra. But if we only have one way to get spectra, then that can present a challenge in how we predict these explosive events. And so what MUSE is going to be is not a single slit spectrograph, but a 35 slit spectrograph. So looking at the sun's corona and looking for explosive events that may very well be similar coronal mass ejections to what the Carrington event was, looking at that, and instead of having to scan the whole field of view like this, it just has to scan the distance between two of those slits and collect spectral information from the entire field of view, which means we get physics for the entire field of view and physics for an entire explosion, which we don't really have very well locked down observationally right now. And so that type of information is crucial for understanding how to predict these space weather events. And so we're super excited about that.
Yeah. So what sort of warning do you have? Obviously, the photons take about 8 and a bit minutes to get to us. This is a plasma release. And so how long have you got? And is the idea then, if you get sort of Carrington 2.0 going off, there is a little bit of warning to unplug your laptop.
Right. So of course the mass is not moving at the speed of light, and that's good for us. Typically, you get anywhere on the order of 14 hours to a few days, depending on how fast the plasma is moving, which of course is dependent on how massive it is and how much energy release was in that reconnection event that launched it in the first place. So you have a little time, I guess, to do what you love. And then,
I'm going to add with this because this is interesting, and I'm not sure what the answer. We have a question from Bunsen burner, maybe relative of the person who invented the Bunsen burner. Has anyone ever heard an aurora? That is, the effects that this storm that is, interacting with the air molecules in a dramatic way. How is this recorded sonically, and is that a thing? And
now, yes, like? Okay. The answer is yes. Observationally, yes. People have reported hearing the aurora. Now, there's a couple of things. You can sonify any type of data you want, basically. You can take data that is not available in the wavelengths or frequencies we can hear and convert it into frequencies that we can hear. That's not what I'm talking about. People do that. I believe someone on the Cassini team, I think, has sonified Saturn's aurorae as well, so you can listen to those. But that's not what I mean. People have reported hearing sounds and crackles from the aurorae. Now, that only makes sense to me in the context of induced ground currents. The aurorae are happening quite far above our heads, many hundreds of kilometers, right, above our heads. And so the speed of sound is quite slow. So hearing aurorae in live time, first of all, doesn't make temporal sense to me. However, hearing the effects of the aurorae on an induced ground current system next to something that relies on that system makes that
okay.
So that has been reported many, many times over many communities. And it is one of the great things about Aurora is that it depends so much on citizen science and citizen science observations. Some of the most prolific Aurora chasers are not people that professionally associate with the science behind auroras. And scientists depend on these observations all the time. One of the great projects of our time in terms of aurora chasing is called Auroras. This is a citizen science initiative that has led to phenomenal aurora-based scientific discoveries based on citizen science observations. So yes, people have heard the aurorae. Yes, they have seen auroral forms that hadn't been observed in a really long time and have not been observed scientifically until they said something. And so this is a really exciting way to get involved if you're living or traveling to an area that experiences a lot of aurorae. This is just a wonderful opportunity to submit your observations so that we can get better at not only predicting from the sun side, which is what my people do, but predicting from the ground as well. What we should be seeing.
Excellent. And definitely just go into Google and Google Aurorasaurus, a type of strange atmospheric dinosaur, and take a look at what they're doing, which is fascinating. Becca, thank you so much for giving us an update on this perfect storm in space. Wonderful to chat to you. We are the SETI Institute. Thank you very much for tuning in. Thank you very much for your questions. We are a non-profit organization, as you well know. So any donations would be gratefully appreciated to continue the work, either SETI Live or the science that's going on here. I will be back on Thursday for the next SETI Live. We have Melissa McClure from Leiden University talking about the dawn of a stellar system. We're looking at a solar system being born. So that's going to be very, very exciting indeed. Becca, thank you. Thank you everyone for tuning in, and we will see you soon.